All right, hello, welcome back to chapter 6. So, in our brand new chapter in our table of contents, we are first going to talk about simplifying radicals. So, if you want to add simplify radicals to page 70 right here, we're going to set up this page and I'm going to show you how, and we're going to do it together in just a moment. So, simplify radicals, page 70, let's do it. Okay, so first things first, you should have a small one like this. This one's just going to get folded right in half. Take a couple notes on the top of that. That can kind of go in the top left corner of page 70. Now the other one that you have should look like this. You'll notice this line up the center. We're going to cut that in half. So like we're fully cutting it in half. And then of your two halves, you're going to want to look for the like the black heading that says combination first. So combination. And then after that, we want the one that says variable expression on it. And you're going to scooch that right above combination. So you're looking at it like this. And then if you go right above these problems here and sort of fold down, you should see our other two headings appear, so numerical and then simplifying radicals. And we can squish that down and then get a staple in it so that those pages stay together. Oh no, Flaminkin's out of staples. Well, I'll staple it after, but you might want to staple it now. And that can go right below this. Okay, so first things first, what the heck even is a radical? Well, a radical symbol looks like this. Normally we refer to those as square roots, but as we're going to quickly figure out, there are other types of roots as well. So like the general name for this thing is a root or a radical. When you put numbers inside a root or a radical, these inside numbers, I'll usually just call it the inside number. It does actually have a proper name. It's called a radicand, which I'm surprised I don't use more because it's kind of a cool word to say. It's kind of a fun word to say, radicand. And if you're a Lord of the Rings fan like me, it might make you think of Radagast, which is a very cool wizard who rides a sleigh pulled by bunny rabbits. I'm not making this up. Go look it up. Radagast, Lord of the Rings. It's amazing. Even though radicand is a cool word, I often don't use it. I usually just call the inside number the inside number. And then we'll probably be talking a lot about the outside number or like a front number. I guess this has a proper name as well. It's probably a coefficient, but I'm really just going to refer to it as the outside number. Now here's the new thing. With our root symbol, as I said, kind of looks like division with a little check mark. Sometimes I'll put a little end on it to know that, okay, this is where the root ends. We are going to find out that there are different types of roots that we can take. And so to let someone know we're taking not a square root, but a different root, right in this little check mark area right here, you might see a little baby number. And that little baby number is called the index. And that index is telling us what root to take. Now, if you don't see a number, then it's just assumed to be 2, but we can take a square root or the second root. You can also take the third root or a cube root. We could take a fourth root, a fifth root. You can take any kind of root that you want. And they kind of work the same way that a square root does. So like when I'm taking the square root of 25, I can do that because I can split 25 into 5 and 5 because 5 times 5 is 25. I can't take the square root of 27 because there's no way to split up the 27 evenly, like the same number times itself to get 27. Now there are other ways to split it up that we're going to talk about in a minute, but if I'm taking a cube root, I can't take the cube root of 25 because a cube root would need to be split up into like 3 equal numbers. And 25 just splits up into 5 and 5. I can, however, take the cube root of 27 because I can split 27 up into 3 times 3 times 3. So like 3 times 3 is 9, times 3 is 27. So the cube root of 27 is 3. So that's kind of how a cube root works. A fourth root works the same way. You're going to split a number up into 4 equal numbers. So like a really good fourth root is 16 because 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2. We're going to talk lots about how we simplify radicals, that you can't just square root or cube root or fourth root. We've actually talked about it before a lot. This is where we use our birthday cake method. So we're birthday caking to split things up and take stuff outside the root that we can take outside and leave stuff inside that has to stay inside. Okay, so let's start easy with numbers first. If we open this up, we should be looking at only numbers. And some of these I'm going to change up a little bit. So right now, if you look at them, they're all square roots. But I might add an index in there to talk about a different root. But we'll do the square root of 12. So with the square root of 12, I don't know it, but I can birthday cake it. So if you remember, we put 12 inside the bottom tier of our birthday cake. And then we think of a prime number that can go into 12. So choose real good. 6 times, and then we just divide. Another prime number that goes into 6 is 2. 2 into 6 is 3. Prime number that goes into 3 is 3. And then we end with our birthday candle on top like we want. When we're taking the square root, we're looking for the buddy system. So we want a pair. And so I take out a 2. And then anybody who doesn't have a buddy has to stay in. So 3 would stay in. So 12 simplifies to 2 root 3. Let's try the square root of 27. So we said we couldn't take the square root of 27. However, I could probably birthday cake it. So a prime number that goes into 27 is 3. 9 times. And 3 goes into 9 3 times. And then 3 goes into itself 1 time. So birthday candle. And again, we're looking for groups of 2. So 3 would come out. Other 3 would stay in. Okay, square root of 50. I don't know, but I can birthday cake. So 50 would go here. Prime number that goes into 50 is 2 for 25. 5 for 5. And then 5 for 1. And since we're looking for the buddy system, we can take the 5 out and leave the 2 in. Okay, so now let's try a different type of root. So I know this says square root right now. If I put a little smidgy 3 in there, the little index of 3, now we're going to take the cube root. Okay, so the cube root of 32, I do not know, but I can still birthday cake it. So we go 32, and then we want a prime number that goes into 32. So 2 works 16 times. Prime number that goes into 16 is 2, 8 times. 2, 4 times, 2, 2 times, and then finally 2 into itself once for my birthday candle on top. Now, hopefully this makes sense. When I take a square root, I'm looking for groups of 2. When I'm taking a cube root, I'm looking for groups of 3. So we're going to take this group of 3, and 2 comes out. Now I have a cube root, so I want to make sure I put my little baby 3. And these 2 2s still have to stay in. So a 2 and a 2 are both in, which is a 4. So whatever you group up, you just put that number out. Whatever's left, you have to multiply together. Okay, let's try 200. Go back to a square root. So let's do 5, which is 40, 5, which is 8, 2, which is 4, 2, which is 2, and then 2, for 1. And since we're taking a square root again, we're looking for groups of 2. So a 5 and a 2 can come out. So since a 5 and a 2 are out, that's 10. And then a 2 is left. Let's try a cube root on this one. So we do the cube root of 175. We're going to start with 175. I feel like 5 is a really good number to go into that. 35 times. Then 5 goes into that 7 times, and 7 goes into itself 1 time. So now that I'm looking for a cube root, I'm looking for groups of 3, and I don't have a group of 3, so they're all just staying in, which means that this kind of didn't simplify. It's just still the cube root of 175. Let's try a 4th root on this one. Excuse me. Okay, so we're going to take the 4th root of 1,200. We're going to birthday cake that because I have no idea. So we'll try a 2, just 600. And then I can go another 2 for 300. And then another 2 for 150. And then another 2 for 75. And then I can't go 2 anymore. But we can go 5 for 15. 5, which is 3, and then 3 for our birthday candle. And then, because we're taking a 4th root, hopefully it makes sense that we're looking for groups of 4. And I do have a group of 4 2s right here. So the 2 comes out. And then 5, 5, and 3 are all left in because I can't make another group of 4. So 5, 5, and 3, that's 25 3 times, so that's 75. And then we don't want to forget that this is a 4th root. I'm going to leave the 675. Let's jump on to some variable expressions. So it's a little weirder maybe when we're just looking at letters and there are no numbers. So we want to think about how we would take square roots of that or cube roots or 4th roots. And so looking at just the square roots along the top here, we want to try to look for a pattern. So like hopefully we know the square root of x squared is x. But even if we didn't, I can write x out like x times x. I can write x squared out as x times x. And since we're taking the square root, we're looking for groups of 2. So x would come out and nothing is left, so nothing would be on the inside. So we can use that same thinking for x to the 3rd. So x, taking a square root, so group of 2, so one x is out, this other x stays in, he does not have a buddy. Okay, x to the 4th, so we'd have 1, 2, 3, 4 of those. And since we're doing a square root, we want groups of 2. So 2 x's can come out, so really x squared, and nothing is left in. X to the 5th, we'd have 1, 2, 3, 4, 5. And because we're taking a square root, we want to make groups of 2. So 2 can come out and 1 stays in. Let me circle up my answers here. And then here we have x to the 6th, though. 1, 2, 3, 4, 5, 6, and we're making groups of 2. And maybe you're noticing a pattern that really all I need to do is divide by 2. And if it divides evenly, there's no remainder, like there's no root left. But if it does not divide evenly, then there's 1 left on the inside. Okay. So I feel like we can do these pretty quickly now. And again, we're going to keep this top row all root 2's. So like really we can just use our shortcut now and divide by 2. So if I divide by 2, then that's 1x. And if I divide by 2, that's y to the 4th. Now here when I look, I notice I'm not going to be able to divide evenly. So I'm going to write my root down because we are going to have some left. So like 2 goes into 3. Evenly 1 time, so 1 comes out, but then there's 1 left over, so 1 goes in. I can divide 2 into 6 evenly 3 times, with none left over, so none go in. And then z is to the first power, which 2 into 1 doesn't go, so z is just left in. Okay, still taking the square root, so I notice that I am going to have some left, so I'm going to put my root. And then 2 goes into 4 evenly twice with none left over, so no x's inside. 2 goes into 5 evenly 2 times, so 2 comes out, but then there's 1 left over, so 1 goes in. Now in this bottom row, I want to change it up a little bit, so we're going to do to the third, or I'm sorry, the cube root on these two, and then we're going to do the fourth root on this last one. So hopefully it makes sense. If I'm doing the square root, I would divide by 2. That if I'm doing a cube root, I would divide by 3. So same sort of idea. If I divide 3 into 1, it does not go. So nothing comes out, and that 1x stays in. Oops, I need my little baby 3 right there. If I divide 3 into 4, it goes evenly once. So 1 comes out, but then there's 1 left over. 3 does not go into z, so z is going to stay in. Okay, same idea here. We're dividing by 3 because we're taking a cube root. I think I'm going to have some left over. So 3 goes into 7 evenly 2 times, but 1 left over. It's like 2 times 3 is 6. 1 more for 7. And then 3 goes into 5 evenly once, but then there's 2 left over. So 2y on the inside, or y squared rather. And then last but not least here, if we try a fourth root, again, hopefully it makes sense that if I'm doing a fourth root, we're going to divide by 4. And so 4 will not go into 1, so that x is going to stay. But 4 goes into 9 2 times evenly with 1 left over. Okay, so when numbers are by themselves, we birthday cake. When letters are by themselves, we can kind of just divide. But when we have a combination, our brains have to work both ways. So for the number, I have to birthday cake. For the letters, I have to divide. So I always like to divide first because it's a little bit easier. So if I'm just taking the square root here, I can see that 2 will go into both of these evenly. So 2 goes into a squared once, so 1a, and 2 goes into b to the 8th 4 times. But then I have to birthday cake the 40, and so 2 will go into that 20 times, 2, 10, 2, 5, and then 5. And so because we're taking a square root, we're looking for groups of 2. So 2 comes out, but 10 is still in. Okay, same sort of idea with 18x to the third, y to the fourth. I like to do it in 2 parts. I like to think about the variables first because they're easier. And since we're taking a square root, we're going to divide by 2. So 2 goes into 3 once, but there's 1 left over. And then 2 goes into 4 twice with none left over. Ooh, I should have left a little space there because if there's a number left over, gosh darn it. Oh well. Now we're going to go birthday cake 18. So 2, 9, 3, 3, 3, birthday candle. So a 3 is coming out, but a 2 is going to smush in. Okay, let's maybe save the rest. The multiply ones, I really don't want to worry about just yet. Maybe we try these 2 on our own. Yeah. All right, I'll see you in the next one.